So last time we defined certain numbers, but more importantly we defined what it means for a set to be inductive, and then we defined n to be the smallest inductive set. So this is the definition. It contains all of those things that are in every inductive set, all the things that are necessary for inductiveness. And then after defining n like this, we proved that n is an inductive set and that it's the smallest one. So what this enables is this theorem, mathematical induction, which is a technique that we will pretty much use, and people pretty much use, anytime they want to prove that natural numbers have a certain property. Even if someone is not directly using induction to prove that natural numbers have a certain property, they're probably using it somehow in the background, like maybe they're using a result that was proven using induction. So in this video I want to go over the statement of this theorem and sort of how to use it. So I'm going to state the theorem here step by step, and I'll start by filling it in by using an actual sort of placeholder proposition other than just a Greek letter, capital Phi. I'll put in an actual thing that sounds like a proposition. So let's suppose you'd like to prove that all natural numbers have a certain property. So you have some property in mind that you want to prove all natural numbers have. As a placeholder, I'm going to use being green, just because that's something I've been using. So let's say you want to prove that all natural numbers are green. So that can stand for any property that you're trying to prove they all have. So for all n, natural number implies n is green. So let's suppose you want to prove that. Then mathematical induction provides a way for you to do it. So it says, okay, if you can prove this and that, which we're about to say what these are, then you can deduce that all natural numbers are green. So this is giving you a way to prove that all natural numbers have a certain property. All right, so here's the idea. First, you need to prove what's called a base case. So prove 0 is green. Prove that 0 has that property that you're trying to prove all natural numbers have. And then prove what's called an induction step. So prove that for any given natural number, if it has the property, this is a hypothetical, if it has the property, then the next one, its successor, also has that property. So if you imagine that the collection of natural numbers consists of things like 0, the next of 0, the next of that, the next of that, and so on, then being able to prove number 1 means you've proven that this is green. Being able to prove number 2 means that you've proven sort of in one go an infinite collection of statements, right? That's the power of having a variable here. In one go, you've proven sort of an infinite collection of statements, like if 0 is green, then 1 is green, and if 1 is green, then 2 is green, and if 2 is green, then 3 is green, and so on. If you manage to prove this with a variable n here, if you manage to prove this for all, then you've proven sort of that infinite collection of statements. So you've proven that 0's greenness implies 1's greenness, and you do have that 0 is green from up here. And 1's greenness then implies 2's greenness, which implies 3's greenness, and so on. So what this is basically enabling is almost an infinite collection of conclusions coming from an infinite chain of implications. And all you need is something that starts the chain of implications, which is the base case. So this is called base case. And something that drives the implications. So by using a variable in this position, it sort of gets you all of these implications. It doesn't make sense to put implication symbols here, but you see what I mean. This is green implies this is green implies this is green, and so on. So this is called, number 2 here is called the induction step. So this is the statement of the theorem mathematical induction. Now, if I leave the statement like this, then it's not actually a very useful theorem, since it's specifically about greenness, which is not a real property for numbers. What we would rather have is actually something more general, where you can fill in any property. Like instead of is green, is whatever you want. Just fill in whatever you want. Then it will be a useful theorem. And that is what's achieved using the Greek letter phi here, and the variable x as sort of a position that can get replaced, a blank that can get filled in by different things. So let's look at this step by step. Let's say instead of is green, you want to prove something else. So let's consider phi to be a stand-in for n is green, but actually I'm going to make it a stand-in for x is green, so that I have this x that's not related to n or 0 or anything else that I'm going to replace by different things at different positions in this theorem statement. So all I'm doing here is I'm going to replace things by the version of them that lets you put the version of them that doesn't focus specifically on greenness. So instead of n is green here, I'll put phi with x replaced by n. So if I just put phi, it would be x is green, which is not what I'm trying to say. Okay, and here I'll put phi with the x replaced by 0, right? Then this would say 0 is green. And then here, what we need to prove is for all n, if the property phi holds for n, then it holds for next n. So, okay, before I erase these, look at what they are. This says n is green, this says next n is green. So this one will be phi with the x replaced by n, phi with the x replaced by next n. And this is supposed to be for all natural numbers n, not for all n. That was actually a mistake to exclude that. So even originally, before I made the changes here, this is actually not correct. It should say for all n, if n is a natural number and n is green, then next n is green. That's what you would need. Otherwise, you would have to worry about other green things that are not natural numbers. But this whole thing is about specifically natural numbers. Okay, so let me fix that. So this is how the induction step should look. It should say, if n is a natural number, then the greenness of n should imply the greenness of next n. This is the induction step. Then you may deduce that for all n, phi holds for n. N is green, if phi is this. Okay, so now you can take phi to be anything. It doesn't have to be x is green. It could be any statement about x, and you can think of that as sort of a predicate, a property. A property that you'd like to prove all natural numbers have that property. So as an example, phi could be the proposition x is green. Then you would be trying to prove that all natural numbers are green, and to do that you would prove 0 is green, and then you would prove that for any given natural number, if it's green, then the next one is green. Phi could be x is either even or odd. Then what you'd be trying to prove, then you might be trying to prove that every natural number is either even or odd, that it has to be one or the other. So phi would be x is even or x is odd. then the way to do that using mathematical induction will be to prove that 0 is either even or odd, and then prove that for any given natural number, if it's either even or odd, then the next one is either even or odd. Then that would let you deduce that all natural numbers are even or odd. So here's another example. Phi could be the sum of the integers from 1 to x is given by this formula, x times x plus 1 over 2. And this is actually a property of natural numbers, just like greenness. This is a property of natural numbers. It's just hard to describe using a noun like greenness, a noun that gives you the abstract concept. But this is a property that natural numbers can have. A natural number could have or not have the property that the sum of the integers from 1 to it is given by this formula. Then suppose you'd like to prove that that's true for all natural numbers, that for all n the sum from 1 to n is this. Then one way to do that is to prove that it's true about 0, which, okay, that's a little bit weird since we'd have to make sense of what it means to have a sum from 1 to 0. How about I start it from 0? That's harmless, right? Okay, now it makes more sense. First prove that the sum of the integers from 0 to 0 is given by this formula. Then you would have to prove that for all natural numbers n, if the sum from 1 to n is given by n times n plus 1 over 2, then it follows that the sum from 1 to n plus 1 is given by that formula. Then you can deduce that the formula works for all natural numbers. Here's another example. Phi could be every vector space of dimension x has a basis. So this would be, this is a property that natural numbers could have or not have, right? Every natural number x could either have this property that every vector space with that natural number as its dimension has a basis, or it could fail to have this property if there's some vector space with that natural number as its dimension which does not have a basis. Then to prove this statement using theorem 94, so to prove that for all x, for all possible finite dimensions, so in other words, if you want to prove every finite dimensional vector space has a basis, then you can prove that every zero-dimensional vector space has a basis, and then prove that for any given natural number n, if it's true that every n-dimensional vector space has a basis, then one can prove as a consequence that every next n-dimensional vector space has a basis. Then you can conclude that every finite dimensional vector space of any dimension has a basis. So this is really very versatile, a lot more than you immediately might think if you just think about like simple properties like has this one adjective applying to it. And the extreme versatility comes from the fact that phi really could be any proposition. So when you actually go to use this theorem, say you want to use it to prove that for all natural numbers n is green. When you actually go to use it, here's the format that I will suggest that you follow and that I will follow when I write things. Basically, split your proof into two parts, a base case and an induction step. This makes sense because you need to prove a base case and an induction step in order to use this theorem and get this conclusion that you want. By the way, in case this wasn't clear, I'm not talking about proving this theorem. I'm talking about using it. So after it's proven, then it becomes available for us to use. So when you're working on anything that comes after theorem 94, you can use theorem 94. So what I'm talking about here is when you use this. When you use this, you need to prove that one holds for your particular situation, your particular choice of phi and x and everything. And you need to prove that 2 holds in your particular situation. Then using theorem 94 means you get to conclude this. So say you want to prove all natural numbers are green, then your phi is x is green, right? So here's phi with the x replaced by n. Then to prove this, you prove your base case, so prove that 0 is green. So somehow put your argument there. Then And don't forget this part. These parts are all important. So assume n is a natural number and assume n is green. Then try to prove that next n is green. So where are these coming from? They're coming from, if you want to prove this for all, you do it by universal generalization, right? So you consider any n which is a natural number. Consider any natural number n. Then you need to prove this implication. So you assume n is green. Then you try to prove next n is green. So that an induction step will always be structured that way. It's just that is green will be replaced by different things. And then when you're done with both of those, then usually you can just stop, but this is what the conclusion sentence would be if you really want to include it. By induction, so by theorem 94, this theorem here, it follows that every natural number is green. Okay, so we're going to use this a lot today. We're going to use this theorem a lot today. But in terms of proving this theorem, I'm going to consider that to be not part of the core content. It's a little bit less important, although I think it is important to have the full story. But I'll leave the proof as sort of optional material at the end of the lecture, so that if you want to tune out at some point, that's what you miss, rather than the more important stuff where we use this theorem. In case you don't watch that part where we prove mathematical induction at the end, which is fine actually if you want to read the proof here is perfectly fine. But let me just make some comment about it that everyone will see. The proof of theorem 94, the proof that mathematical induction works, is going to make heavy, heavy use of theorem 93. So that's where the definition of the natural numbers comes in, right? So theorem 93 uses definition 92. That's where this stuff matters. Pretty much, you'll never use theorem 93 or definition 92. You'll almost never use those. You'll almost always instead use theorem 94, which has sort of used these for you. So, yeah, just in case you missed that point, when you use theorem 94, in those moments you can appreciate the way natural numbers are defined, since it relies on that.